All right. So today I'm going to discuss a project at the intersection between databases and natural language processing. And this project connects to the good old saying, when all else fails, read the instructions. And there's some truth to this statement because if we, for instance, want to get the maximum performance out of a database management system such as Postgres, one might be tempted to try out different settings and to observe what performance we are getting from it. But probably it's a better idea to first have a good look at the manuals, and perhaps not only at the manual, but also at some associated blog entries and discussion forum entries in order to avoid having to randomly try out things in order to find good configurations faster. And in this talk, I'm essentially transferring this piece of wisdom to automated database tuning, where we have some kind of tool which tries to find optimal parameter settings to optimize performance. And that might sound a little bit far off. I mean, here I'm essentially suggesting to read the manual and blog entries and so on by automated means. But there has been a lot of progress in the domain of natural language processing recently. And so perhaps you have seen some of those headlines, in particular about the recently released GPT-3 system, which is a very large neural network for language processing. And people have found out that it works actually quite well across a range of application scenarios. So now I'm proposing to use this for the domain of database tuning. Now, to give a little bit of background, among the technologies that enable those advances in natural language processing over the past years is in particular the so-called transformer architecture, which is an architecture for neural networks that, among other advantages, allows you to scale up training more easily. And that has enabled the creation of very large neural networks such as GPT-3 with hundreds of billions of parameters, basically, which focus on language processing. Now, the way those models are used is typically in two phases. First of all, you have the so-called pre-training phase. And for the pre-training phase, we use some kind of task where large amounts of training data are easily available. That could be, for instance, trying to predict obfuscated words in web text. For that, you can easily exploit all kinds of text as training samples. And after this pre-training step, which is extremely expensive and takes a long time, it is fortunately relatively easy to specialize those neural networks for new tasks, such as trying to translate natural language questions into SQL queries, because they have gained some high-level natural language understanding capabilities. It is relatively fast to specialize them to those a little bit more specific tasks. So now I'm proposing to leverage this for the domain of database tuning. And that essentially means that we want to find optimal configurations, meaning optimal assignments from database system parameters to configuration values in order to optimize performance for some input workload according to some user-specified metric, which could be, for instance, maximizing the number of transactions that are processed per second or minimizing the amount of runtime that certain queries are taking. Now, this problem is difficult because typically database management systems have hundreds of configuration parameters to tune. Also, different settings have significant impact on the performance that you see, and the default settings, they're often suboptimal for specific workloads and metrics. So doing this by hand is extremely difficult, which is why people have been working a lot on trying to automate this kind of tuning. And one recently proposed a method, the DB-BERT method, which is kind of representative for the type of approach that you would use in this context, uses reinforcement learning in order to find good parameter settings. So this is the high-level picture, how that works. The input is a workload that you want to optimize and the performance metric according to which you want to optimize. The output is the best configuration it has found. And in order to find configurations, the system essentially selects parameter settings then tries them out by evaluating the input workload with a database management system that is being tuned and measuring the performance that you're getting from that. And it does that iteratively, trying out different parameter settings and hopefully finds better settings as time goes on. Typically, the way in which the system selects parameter settings to try out, that is based on reinforcement learning, which is a learning variant that essentially allows a system to select itself what it wants to learn from. And this is used in order to select which parameter settings to try out next based on the previous experiences. So that is the state of the art. This is a recently proposed system. But there's a couple of limitations. I mean, first of all, tuning takes a lot of time. So this tuning process that you saw there, depending on the workload we tune, that might take multiple days of tuning time and execute many hundreds of iterations of the tuning. And also, typically those methods assume that users provide quite a bit of input in order to narrow down the search space for tuning. For instance, selecting a small subset of configuration parameters to tune and selecting somewhat reasonable value ranges for those parameters. And then the system only explores the space within those constraints. And then I'm putting this in parentheses because we don't even expect those tools to do that. Of course, the system is a black box from the perspective of the user. It will propose some parameter values, but it won't provide any kind of explanation about why those parameter values work better than the default settings. It turns out, oh yes, please. Oh, no, not at all.
So I just had a quick question on what you're doing as your reinforcement. Is it just like least squares to the thing closest to the parameter?
Okay, that's a great question. I'm going to provide a little bit more details about how reinforcement learning maps to this problem, but to already give you a quick intuition. So in reinforcement learning, you typically have some kind of agent which explores some environment and is essentially trying to maximize a reward function. And you are essentially asking what is the nature of this reward function. The nature of the reward function depends on the metric that we're optimizing for, which is provided by the user. If the user selects, for instance, I want to minimize runtime, then the reward metric would be based on how much time you save compared to the default configuration for the same workload. So if you, in the simplest version, that could be, I'm saving 10 seconds of time compared to the default settings with those parameter settings. So I get a reward of 10, for instance.
So are you only able to work in one parameter though? So can you, so like if, for example, you want to run a training model on runtime, but also storage state, is there, does the model only work on one of those metrics, or does it work on both and kind of creating the aggregate of like whatever?
If you have like a composite metric between two things, basically,
yeah,
that would also work. I mean, so you could define a reward function that, for instance, I mean, let's say, I'm not sure if that is what you mean, but I mean, for instance, we could say we have a constraint on storage because we only have that much space on our hard disk. So we could say that the reward function is just returning a reward of 0 or even negative reward if we are exceeding the storage space constraint. If we are staying within the storage constraint, then the reward function returns the reward that is proportional to the time savings, for instance.
Gotcha.
And similarly for instance, optimizing transactions per second. In that case, you can just use the throughput as the reward metric. Yes, please. Great question.
Just like when you're letting like their agent run, do you let it say like, oh, we're gonna let it run for 24 hours, or do you find like a stop criteria, like when performance has been improved by X%?
That's a great question. That's a great question. So you can do both. I mean, at this point, I mean, for our system, you specify a number of iterations. But there's like other systems and you could easily change it in order to work with a stopping criterion that, for instance, says something like, if the average execution time did not improve by more than X% in that many iterations, then stop and assume that you have probably found the optimum. Yeah, but that's a great question. You could experiment with different stopping criterions. Actually, we are, okay, strictly speaking, we are supporting a number of iteration limit, but also a time limit, whichever is hit first. But you could easily add some more complex stopping criteria. Great questions. Okay, so those are limitations of the state of the art here. And it turns out that in order to overcome those limitations, a lot of the information you need is already available. The only problem is that information is typically available in the form of natural language text. For instance, if you go to those database administrator online forums like DBA Stack Exchange, for instance, you find lots of discussions where people are giving hints. Oh, in this scenario, for this type of workload, you probably want to set this parameter to that value, for instance, right? So there's lots of interesting hints available online, also with an explanation for why it works and so on. The problem is just that so far, we weren't really able to leverage this kind of information for automated tuning tools. Now, we recently did some work where we tried to do text mining on this kind of a text in order to extract the important tuning hints for improving database performance in specific scenarios. So we had a first work in that space, which essentially just uses text mining to extract all kinds of tuning hints from lots of text documents that we find on the web. So this is a one-phase approach. So you provide us input the text documents, then it extracts hints about how to set specific parameters, and then it recommends them basically. Now, this is a relatively simple version. It comes with a couple of limitations. First of all, those tuning hints are often interesting, but they're not always directly relevant to your specific workload. And sometimes they're just plain wrong. So this original prior system that we did, it cannot deviate from the tuning hints that it finds in text, and it cannot specialize to specific workloads and tuning metrics. Also, it uses supervised learning, which means that it requires quite a few hand-labeled training examples, which are tedious to generate. So this is why we continued working on this and came up with a DB-BERT, which is a system that uses hints mined from text documents, but on the other side, it just uses those hints as a starting point and then does reinforcement learning-based exploration and tries out configuration settings with the database management system and measures the performance that it gets. So that is the DB-BERT system, and in the following, I'm going to explain that in more detail. Now, to make things a little bit more concrete, those are the types of tuning hints that we are looking at. Here you see a few examples from the Postgres database system manual, as well as from several online blogs. And for instance, here the first hint recommends to set one specific parameter, shared buffers, to about a quarter of main memory. The second hint recommends to change the random page cost to an absolute value, right? And the third one recommends to use a certain degree of parallelization. Here really comes the first challenge. The first two hints, they specify explicitly the name of the configuration parameter that you want to set. The last one just says that we should have a degree of parallelism of 6, but it doesn't tell you what is the name of the relevant parameter, so we would have to infer it in this case. Also note that the first hint is relative, meaning that it recommends the setting for shared buffers as a percentage of the amount of RAM available. The second hint is absolute, meaning that it recommends a concrete value for that parameter. So in order to exploit those hints for automated tuning, first of all, we want to translate them into formulas. Those formulas might depend on system properties such as the amount of RAM available. In the first case, for instance, the hint is to set shared buffers equal to 1/4 of RAM. In the second case, we are setting random page cost to the value of 1. So those are the types of tuning hints that we're interested in. And the structure of those tuning hints that we are generally supporting essentially consists of 3 parts. The first one is some kind of a value that is mentioned in text. The second part is optional and corresponds to some system property, such as the amount of RAM, the amount of disk space, and the number of cores. And the last part could be a constant that allows us to deviate from the recommended value by up to factor 4, but not too much either. So this is the format of the hints that are currently supported. And this is an overview of the system. You see that it gets as input user-provided workload to optimize metric to optimize for, and some natural language keywords, which allows it to find relevant text documents that it will mine for tuning. The output is again the best configuration. So at a high level of abstraction, we start by retrieving relevant documents from the web. Then we try to extract potentially useful hints from them, and we try to prioritize those hints in order to decide in which order to process those hints. Now, in the next step, we are trying to translate those hints into formulas, and we might try to adapt those hints, meaning to deviate from the recommended values. Sometimes different hints from different sources can be conflicting. So in those cases, we want to assign weights to different hints, which essentially determine which hint wins if we have multiple conflicting hints. Finally, we evaluate configurations that we create based on those hints. And from the performance we observed, we learn to select better configurations and to translate hints better in the coming iterations, because the second part of the system, the learning phase, is iterative and will be executed until the time runs out or until the number of iterations reaches a limit. The first part, the pre-processing stage, is only executed at the very beginning of the tuning session. For the following, I'm going to discuss the pre-processing step in a little bit more detail, afterwards the learning phase. Now in pre-processing, we essentially want to do the following. So we assume that we have given by the user some collection of keywords which somehow describe the tuning goals. So for instance, here, the user wants to tune the latency, meaning the execution time, for a specific benchmark called TPCH, for a specific system called a Postgres. And we can use that in order to issue a Google query in order to retrieve relevant documents from addresses like stackexchange.com or postgresql.com. From each of those documents, we might be able to extract one or multiple tuning hints like the ones that you see here. So we first of all want to essentially take those text passages and extract the tuning hints that refer to specific tuning parameters and recommend specific values. And then finally, we want to assign weights to those hints in order to decide how to handle situations where some of those hints are conflicting with each other. So in more detail, in the first step, we are retrieving documents from the web based on the user-provided keywords. We are extracting text passages from those documents, and then we are splitting the text into chunks of a size that can be easily processed by those language models that we are using. In the next step, we are trying to extract the hints from those text passages, which means that we first of all need to find out which parameter the text passage refers to, which can be easy if the parameter is explicitly mentioned, but it would be much harder if the parameter is only implicitly described. So we are using the list of configuration parameters of the database management system. We are comparing that against the text in those text passages. Also, for those parameters, we need to extract the specification of the recommended value. And after we have done both, we have candidate hints of the type as you see at the bottom of that slide. For instance, here, the hint would be to set max parallel workers to 6. Now, what we could do, of course, is that we treat all of the hints that we find on the web, which is typically thousands of hints. And after we have done that, we start executing trial runs and measure the performance. Now, the problem with that is that analyzing all of those hints with sophisticated natural language processing methods actually takes a lot of time. So when doing this, it would take a while until we have the first performance results that we gain by trial runs. And because of that, the users would have to wait for a long time until the first recommended configurations get returned. So it is probably better to somehow interleave a natural language analysis and trial runs like you see here. So here we analyze a couple of hints, and then based on the subset of hints, we generate a configuration to try out in a trial run. And then we analyze more hints and construct a new configuration that we try out, and so on and so forth. Now, the only problem with this is that maybe when analyzing only a subset of hints, we are unlucky and those hints are not particularly relevant for our scenario, maybe concern parameters that don't have a lot of impact on performance. So also we would lose time. So it would be better to start with those hints that are most impactful for a performance, but it is hard to tell in advance. A simple heuristic that doesn't work too badly is to prioritize hints about parameters that are frequently mentioned, because parameters that many people discuss about on those online forums, those are probably the parameters with most impact on performance. So you could order those hints by the frequency at which the corresponding parameter is mentioned on the web. That is already better, but it comes with another problem, because now the first couple of hints we are considering will probably all be about the same parameter. And that is a little bit boring, because if you have seen a few hundred hints about the same parameter, then probably you cannot learn that much more by considering even more hints about that same parameter. So here, what works better is to mix different parameters. So we still prioritize parameters that are frequently mentioned, but we set a limit of hints that we can consider about the same parameter in a row before we are switching to hints about the next configuration parameter. So this is one example how that would work. So the shared buffers parameter of Postgres, it's very important for performance, and it is very frequently mentioned on the web. So we would first start by considering a few hints for this parameter, up to 2. But after that, we are switching to hints about the next parameter, which is work mem, also an important parameter. And after we have switched to another parameter, we can still come back to the first parameter and consider more hints for the next trial run. But this system, it's a simple heuristic, but it is quite effective at making sure that important parameters are prioritized, but still we have some kind of diversity of parameters that we are considering in those hints. So this is the high-level approach that we will be using here. So here we have fixed an order of the hints in which we considered them, and we interleave natural language processing with trial runs. Now, in the learning phase, we have those phases that you see here below. We essentially have 3 goals. We first of all want to translate those natural language hints into mathematical formulas, which tell us how to set the parameters. We might decide to deviate from the values that are recommended in text, and we might decide to assign weights to different parameters in order to determine their relative importance. Now, for instance, here is an example. We could start with the hints that you see here in the top row of the table. Those are the hints that I have already used as examples before. The first step would be to translate those hints into mathematical formulas, which may depend on system properties such as the amount of RAM. By substituting the values for those system properties in those formulas for a concrete system and resolving the formulas, we come to a concrete value recommendation for each of those parameters. You might decide to deviate from the recommended values for a specific workload. For instance, we could decide to multiply the recommended amount of RAM for shared buffers by 2, and same for the number of recommended workers. And next, we need to determine weights in order to decide on the relative importance of those hints. So here we decide that the hint about shared buffers and setting it to 40% of main memory is by far the most important one. Based on those weights, we can aggregate those hints into one common configuration, which assigns one specific value for each of those parameters. So here you see that we assign shared buffers to 6.4 gigabytes because that is the hint with the highest weight. And we are assigning the max parallel workers to 6. Actually, we might assign it to 12 here. Now I'm looking at the slide because we have decided to multiply by a factor 2. So in each case, we are aggregating all of those hints into one common configuration, which we try out, and then we measure the performance. Here, it's measured as the number of transactions processed per second. And based on what we observed there, we can learn to select better configurations in the coming iterations of the learning phase. Now, it is difficult to use supervised learning in this context. First of all, in order to label passages from a database manual and say how that translates into a hint, you need quite a bit of database expertise, which is difficult for crowd workers, which are typically used in order to label large amounts of data. Also, the way in which we want to translate those hints actually depends on the specifics of the workload in the system. For instance, if we want to decide how to weight hints from different sources or how to deviate from the recommended values. And the same, so this means that we essentially cannot use a supervised learning in this context. And that instead motivates us to use reinforcement learning, which is generally popular for this kind of problem. So in a little bit more detail, a reinforcement learning assumes that we have some kind of agent which explores an environment. And the agent can perform actions on the environment. And from those actions result observations that the agent can use in order to decide what to do next. Also, the environment results in reward values, which essentially tell the agent how good it is doing. So the goal of the agent is to maximize the performance in order to maximize the rewards that it receives. But doing that is difficult because, at least initially, the agent typically doesn't know the dynamics of the environment. More specifically, in the following, we'll be using a reinforcement learning approach that uses a neural network in order to decide what to do next. This is also called a deep reinforcement learning. And when mapping this general outline to the specific scenario that we are dealing with here, the agent that, of course, is the DB-BERT system. The environment is characterized by the workload that we are tuning and by the system properties. The neural network that we're using is based on BERT, which is a very popular language model, so a neural network for language processing. And the actions are related to translating the tuning hints, adapting the tuning hints, and determining weights for those tuning hints. Now, observations are based on the hints that we are finding in those database manuals. And we also will associate labels, natural language labels, with the possible actions that we can take. So I'm going to make that more concrete by an example in the following. And then, as already discussed, the rewards are given for achieving good performance on a workload. And also, before we can even obtain good performance or before we can even measure performance, we first need to ensure that the database management system even accepts our parameter setting. If we, for instance, are trying to set an amount of main memory that is larger than the amount of main memory that we have available, then probably the system will just throw an error. And in those cases, we will get a low reward. All right. So in order to use reinforcement learning, we have to model this problem that we are trying to solve as a Markov decision process, which is essentially a series of states connected by actions. And depending on which action the agent chooses, it decides which state it comes to next. So here we have the states in blue, and actions are modeled as arrows in pink. So we want to do those three things. We want to translate the hint, we want to adapt the hint, and we want to determine a weight for the hint. So now we are dealing with one specific hint, the set shared buffers to 25% of RAM hint that you see on the left upper corner. And by the way, you see that this text passage that I'm showing there at the left upper corner, it actually contains more information than what we are considering right now. We have a hint about the shared buffers, but we also have a hint about the amount of work memory. All right. So now we are
Sorry.
Thank you. Yeah, no, that's great. Thanks. Yeah, very good initiative. All right. So now we are considering the hint about shared buffers. And so first of all, we need to decide whether the hint recommends an absolute value, a relative value, or whether this is not a real hint at all. So that is the first decision that the agent needs to make. Now here, this is a relative hint because it recommends an amount of RAM that is relative to the total amount of RAM that is available. Now, in the next step, the agent needs to decide on how to deviate from the recommended value by choosing a multiplicator. So it could choose to, for instance, double the recommended value, or it could choose to only use half of the recommended value. And after making this decision, it needs to assign a weight to the hint. For instance, it could choose a weight of 0, meaning that it doesn't want to consider this hint at all. Or it could choose a hint of 2, a weight of 2, in order to say that this is rather an important hint. Now, after making those decisions, which only refer to that specific hint, which is marked in red on the left upper corner of the slide, we are stepping to the next hint. And before we're doing that, I should say something about the observations that the agent is making. So since our approach is based on a neural network for language processing, we are making it easier for the neural network to make decisions if we formulate everything in terms of natural language descriptions. So we already have the natural language hint here, which we integrate into those observations. In addition, we assign a natural language label which captures the semantics of each of the possible actions. So here, for instance, for the first decisions, we can just have a text label saying the hint recommends an absolute value, or the hint recommends a ratio of RAM, for instance. And by comparing the hint text to the action label, the system can more easily get an impression for how well a specific choice matches what is recommended in that hint. So this is essentially how we enable the system to make better decisions by mapping all of this into a natural language processing problem. Was there a question?
Yeah, I was kind of wondering about going through this process. What is a good number of hints?
What is a good number of hints? Okay, that's a great question. So I mean, there's like a trade-offs. I mean, if you consider more hints, it takes longer to process them, for instance. So at this point, the system uses, I mean, we have the keywords at the beginning that the user provides. And then the system uses text from the first 100 documents that are returned by a Google search for those keywords.
Oh, wow.
Yeah. So, I mean, that's typically, I mean, a couple of thousands of hints. After various filtering steps, you end up with a couple of thousand hints. And in each iteration, typically, I mean, that's a configuration parameter, but what works quite well is to consider something like 10 hints, 10, 20 hints for each before you do a trial run, basically. I mean, if you do lots of trial runs, then you can try out more things, but it takes a long time. You probably want to consider a few hints before you start making trial runs. And something like 10 to 20 hints per trial run, that works quite well.
Thank you.
Yeah, sure. Other questions on this? All right. So, okay. Oh, yes, please.
We're still limited to just parameters that have numeric settings. So for example, if a parameter has like an enum type text set, like multiple values, then this approach, do you translate that into like a numerical setting for this, or?
That's a good question. So we are not, strictly speaking, limited to numerical parameters, except for the like multiplication step. So I mean, it's true that currently it supports numerical parameters, which also generalizes to Boolean flags, because they can typically be set as 0 or 1. In order to generalize beyond that, I basically would have to cut that middle layer of the tree, which chooses the multiplication. So yes, currently restricted to numerical and Boolean parameters, but one could generalize it. But that's a great point. Yeah, that's a great point. All right. Cool. So this is states, actions, and observations. We haven't discussed about the rewards yet. One first point that I mentioned is we should already be happy if the system, the setting that we are trying out is even accepted by the database management system. It could also throw an error if you're trying to change the parameter value. So this is why the agent gets the first reward for not creating an error when trying out the corresponding parameter setting. All right, so this is all we do for one specific hint here. Now, after making those decisions, we step to the next hint. Here, that hint derives from the same text passage as before, but you see that we now mark up the hint about work mem in red. And about this hint, we are making the same choices, right? Now based on different text. And at the end, we also get a reward if selecting a parameter setting, which is accepted by the database management system. Now we might pass on to the next hint extracted from different text passage. Here it's talking about the degree of parallelism that we want to set. And again, we are making those choices and in the end get a no error reward if the setting that we are selecting is accepted by the database management system. Eventually, after 10 to 20 hints, we are coming to the point where we want to actually measure the performance that we get when setting those parameters in the way that we have selected. So we evaluate those parameter settings by trial runs, which first of all means we have to aggregate the different hints which might be conflicting about the same parameter into one specific value that we want to try out for that parameter. Then we measure the performance that we're getting on the user-provided input workload. And from that, we derive a performance reward, which could be based, for instance, on the number of transactions processed per second or on the amount of time saved compared to the default configuration. And at the end of it, we can use this feedback in order to learn to select the better settings in the coming episodes. Episode here that is a synonym for iteration. And we perform multiple iterations until the time runs out or until the number of iterations reaches a limit. Perhaps a few words about this step here, the aggregation of multiple potentially conflicting hints into one common value. In general, we might end up having conflicting recommendations about the same parameter. Like here for the shared buffers parameter, we have conflicting recommendations that recommend something between 20 and 90% of main memory. And we have decided to assign those hints to specific weights, which we should now consider when making choices about what we actually want to try out in our trial run. So those trial runs can try out multiple parameter settings, but not too many either, because that costs too much time. So typically, I try to select the bounded number of k parameters, of k values, among the recommendations. And I try to select them in a way that we optimally cover the recommendations considering their weights. So more concretely, for instance, let's assume that for the trial run, I'm selecting 30% and 40% of RAM. Those are the two values that I will actually try out in practice. Now here are the hint, the recommendation that is covered least by those two selections. That is the recommendation of having 20% of RAM, which has a weight of 8. So I'm essentially calculating the weighted distance. And here, from the 20% to the 30%, I have a distance of 10, but that is weighted by a factor 8 because I have assigned a weight of 8 to those 20%. So that is a high weight, means this is a really important hint. So this is the distance that I'm getting here. I'm getting a distance of 8 times 10%, meaning 80%. If instead I'm selecting those two values over here, then the maximum weighted distance that I'm getting is between those recommended 40% and the selected 20%, which is a distance of 20%. And I'm weighting that by a factor 2 because this a hint is somewhat important, but maybe not that much important. Maybe the source that I extracted this hint from didn't receive a very high weight in the training process. So here I probably I want to try out 20% and 90% in order to optimally cover all those different suggestions with only 2 settings. All right, so this is the learning phase, and that concludes the discussion of the system. Before I step to the experiments, is there any more questions on how the system works?
I have a question.
What happens if you have like a hint that affects correctness?
Oh, that's a very good point. Yes.
Like, for example, you could change, you know, some kind of concurrency control thing that would affect that would induce transaction, inconsistencies.
That's very good point. Yes, absolutely. I mean, that is something which essentially current methods cannot at all recognize. I mean, from doing trial runs, you typically don't hit a case where you actually encounter incorrect behavior. There are some parameters in a database management system where setting them in a certain way, it often increases performance very significantly, but it also comes with a certain risk, because in certain corner cases, maybe you are, for instance, losing some data, or the database could in principle become inconsistent, right? So still, people are actually quite often choosing to use those unsafe parameter settings just because it makes the database much faster. Now, existing methods essentially cannot recognize that a parameter setting is unsafe. But I mean, that's something that you could quite easily extract from the manual, for instance. The manual will always contain an explicit warning if there's any risks associated with one specific parameter setting. I currently have some follow-up experiments, actually, where I'm trying to extract those warnings from the manual in order to automatically integrate them. What one could say here is that if a specific parameter setting is recommended by a lot of people, it seems that the trade-off, risk versus performance gains, seems to be acceptable for a majority of people. But you're absolutely right that, I mean, that might not precisely match the risk preferences of one specific user. So one extension that I'm currently looking at actually is to extract those warnings automatically from the manual and try to integrate that into the optimization process. In the ideal case, I think the system should actually ask the user, I could get a speed up of like factor 2, but in rare cases, this could happen. Is that okay for you? Then the user can say yes or no, and that decides how the optimization continues. Great question. Yes.
Is there a way to preemptively plan for those edge cases? Kind of, so like you're saying, like, okay, a parameter might break it, but on a 10,000 piece data set, it might break 10, right?
Yeah.
Is there a way to plan for breaking those 10?
That's a great point. I mean, what you should anyway do is like regular backups.
Okay.
So those risks, they're typically not formulated in terms of like how often something, I guess you could formulate them in that way too. The thing is that, I mean, under normal circumstances, most of those risks, they never materialize. But if something happens, like suddenly the power goes out, for instance, right? Suddenly your server crashes for some reason. Then if you have used unsafe parameter settings, you might have some negative effects. And I guess, I mean, depending on it, there's like different types of risks, like many different parameters come with different types of risks. I guess in most cases, the answer would be just make regular backups, basically. Yeah. Or be very sure about like what type of data you're dealing with. For instance, a bank would not want to do any of those optimizations. But if the database just keeps track of, I don't know, the number of clicks on your website, for instance, maybe sometimes a click gets lost. No, okay. As long as the number is pretty much correct, that should be good enough, right? And if that is much faster, you probably want to do it. So it depends a lot on the application. That's generally something to be aware of, frankly, with database management systems. Many people are unaware of those things. For instance, if you use like systems like Postgres, then often the default settings of your parameters, they are actually not always safe. For instance, there's a parameter which decides like how different, how concurrent updates to the database may interact with each other. in your ideal case, everything looks as if those updates have happened sequentially. But in some cases, it can happen that those updates interleave in a bad way, which leads to a little bit strange states in your database. And the default setting comes with those risks, but it makes the database faster. So that's the default setting. But if you ever, I mean, if you have like some really, really important data that you're working with, you want to look in a lot of detail into those settings and make sure that the risk profile that you're adopting there matches what you actually want. Don't rely on the default settings with those things. Great questions. All right, let's discuss a couple of experimental results. So first of all, a couple of words about the implementation. It's implemented in Python 3. And currently, I use the autonomous learning library initially for those experiments that you see here, currently switching to the stable baselines library. And the natural language processing library is called the Hugging Face Transformers library. You also find the code available online. So the focus of those experiments is to show that tuning can be done with few iterations compared to existing methods, that you don't need any manual selection of the parameters to tune or of the value ranges to consider for those parameters. So for the baselines, so everyone considers all the tuning parameters, which is a couple of hundreds of tuning parameters for the systems that I'm considering here. And in order to select value ranges for the baseline, I'm just using like some constant factor around the default settings by trying out different factors. Now, the systems being tuned, that's a Postgres and MySQL on benchmarks such as TPCH, which focuses on processing analytical queries, and TPCC, which focuses on transaction processing. The hardware platform used in the experiments has quite a bit of RAM and a relatively powerful GPU, which is important for natural language processing. Now, I'm comparing like DB-BERT against two baselines that are derived from our prior paper on the topic, which don't use any trial runs. They just rely exactly on the hints that you find in the text documents after extracting them. And the DB-BERT system, which is a state-of-the-art approach which does not use natural language processing to mine tuning hints. Now, the text that is used as input, first of all, here you see how the number of hints that we find about different parameters varies depending on the parameter. So here on the x-axis, you essentially have different parameters. On the y-axis, you have the number of web documents that mention a specific parameter. And as we see here, for instance, for Postgres, that's the line in blue, the shared buffers parameter is mentioned most frequently. For MySQL, that's the InnoDB buffer pool size. And that motivates those heuristics which try to balance the number of hints that we are considering about the same parameter. Now, here are some first results. It's about optimizing TPCH on MySQL. So here on the x-axis, we have optimization time in seconds. On the y-axis, we have the execution time in seconds that depend on the configuration parameter settings that we execute. And so as you see here, as optimization time goes on, DB-BERT quite quickly is able to cut the execution time of the TPCH benchmark into half. So that is a very significant performance improvement, while for the other baselines, that doesn't quite happen because the space of possible settings is just too large. You also see the two baselines that are derived from the prior publication. That is this rectangle in green and a diamond in yellow. And as you see here, the diamond in yellow, that essentially represents a very simple way of extracting hints from text documents just based on keywords. So that one, it's quick to do, but it doesn't improve things at all. The green rectangle represents a way to use supervised learning in order to extract hints from those text documents, which works a little bit better than the default settings, but not that much. And it takes a lot of time. So here you see the effect of actually using natural language processing on all possible hints that we are extracting before we are executing any trial runs. We have,
Sorry,
yes.
Why did DB-PG just not improve at all?
So if you give it long enough, it will improve. So this is a
Okay.
relatively short time frame for optimization, actually. The thing is that DB-BERT innovates actually cheating, so to speak, because it is just using a lot of additional information that it mines from text documents.
Yeah.
If you actually are facing like 200, 300 parameters with lots of possible settings, it actually takes, I mean, you evaluate settings by trying out the benchmark with those settings. It actually takes a lot of time until you find the good settings, right? But I mean, of course, if you have like some text which tells you, hey, try this and that, it goes much faster. So this is what this is basically showing. Similar for a Postgres, same benchmark, same baselines, and pretty much the same results. Now this is TPCH with a higher scaling factor, because for TPCH you can actually choose the size of the database. Here we are multiplying by factor 10, and still we see the same behavior. Now let's switch to TPCC, which measures performance of transaction processing. And again, here you see that DB-BERT is able to very quickly increase the throughput, the number of transactions processed per second, after just a few minutes of optimization time. And here you see, for instance, that like the DB-BG++ baseline also manages to find improvements. It's just not quite as high as the improvements that you can get when having additional information. And again, similar results when executing TPCC on Postgres. One thing that is interesting to do is to compare the configurations that are actually winning for those two benchmarks. That are the configurations that have the best performance and are selected by DB-BERT. And you see that those two configurations actually tune different configuration parameters, and they're actually quite different. And that shows the value of specializing the settings to different workloads and performance metrics. This is performance results for a couple of variants of DB-BERT. For instance, what happens if we don't consider implicit hints? What happens if we don't decide on an ordering between those hints and just consider them in random order instead? And here you see that both of those changes, they actually degrade performance. So that shows that all of those things that we are doing are probably useful. What's also interesting to do is to compare how does the performance depend on the input text documents. So here I'm comparing one collection of web documents, that those are like the first 100 text documents that appear when searching for Postgres performance tuning. I'm comparing that against a more specialized text document, which essentially that's a discussion on a forum named Stack Overflow, where people are discussing specifically how should we tune Postgres in order to get good performance for TPCH, which is exactly the benchmark that we're interested in. So that's just one single document, but it is very specialized to exactly what you're interested in. And indeed, if you use the specialized document, then we can find a good configuration faster than when using all those more generic documents. In the end, both of them converge pretty much to the same solution, but that just shows that if you have tuning text which matches your requirements very well, you can probably get even better performance from DB-BERT. All right. So that was an overview of the DB-BERT system. If you're interested in more details, you can check out the repository. There have been also a couple of publications about DB-BERT and about related topics. Generally, I find the space interesting. This is one first work which tries to connect the natural language processing with database performance tuning. I think there's many more opportunities. For instance, in another recent paper, we are trying to exploit the names of database columns in order to get some first guess for which of those columns might be correlated and what the data properties might be. Good. Thanks for listening. And now I'm happy to take more questions. Yes.
Did you have any issue with the processing speed of Python, or did you have to run through like Cython or something like that, or did you
So-
have no issues with?
Right, right. I mean, like the thing that the bulk of the processing is basically two things. It's first of all the processing of natural language, and for that, I mean, I'm essentially using the Hugging Face Transformers library, which encapsulates essentially it primarily it's based on PyTorch internally, and it exploits the GPU in order to make that efficient. I mean, the other big source of overheads is executing those trial runs, which can take a couple of seconds for each trial run, right? Or even minutes, depending on the configuration. So, I mean, those are the two big sources of overheads. Like the logic which connects that is relatively fast to execute. So there, I didn't see any performance problems with Python.
Yeah, so you just had a strong GPU that allowed for the PyTorch to.
So, I mean, actually, I mean, I can't even execute it here on the laptop. I mean, I mean, it still works, right? But I mean, in order to get optimal performance, you want some GPU in order to speed up the whole natural language processing. You might want to vary the number of hints that you consider before each trial run. I mean, for the server with GPU, I would recommend something like 20 rather. Here on the laptop, I would probably recommend something more like 5.
Awesome.
Yeah.
Thank you.
Sure. More questions?
So if you compare like the configuration selected by this to maybe like one that a human actually selects, like is a human still able to outperform like these kind of systems, or?
I would like to make that experiment at some point. I mean, one has to say that, I mean, there has already been some experiments that compare the performance achieved by automated tuning and the performance achieved by human database administrators. And it turns out that those tools can often find better settings, actually. So nevertheless, I think that would be an interesting comparison. I mean, in a way, I mean, like, although especially since this is exploiting a lot of like natural language processing, given enough time, if you go through all of those forum entries and try those things by hand, you should be able to find the same configurations. Yes.
You might have said this and I just missed it. I think you actually did. But in terms of like when it's kind of that optimization is getting total stagnation, is there any like kind of trade-off between like exploration and like exploration and exploitation? Or does it just keep on going with whatever frame? Does it always just go based solely off that?
That's a great point. Yeah. I mean, yes, there is a trade-off between those two. I mean, that's like one of the primary contributions of reinforcement learning, managing this trade-off between exploration and exploitation. To provide a little bit of background. So when making those decisions, when trying out things, right, you could always have, basically you could decide, okay, there's like certain settings that seem to work quite well. So let's try out something which is very similar to those settings. That would be exploitation, because you're exploiting things that you have seen before. On the other side, you could say, hey, I'm curious, let's try out something which is very, very different from everything that I have seen so far. That would be exploration, right? And there's a tension between those two. If you try out completely random things all the time, then probably you won't find something good that quickly. On the other side, if you stick always very, very closely to what seems to work well currently, then you might miss some big opportunity because it's different from what you have seen so far, right? And reinforcement learning algorithms, they have very sophisticated statistical methods in order to manage this trade-off, right? And to sometimes try out something which is quite different, but also sometimes trying out something that is quite related. So that is an important component in order to make this whole approach work. And yes, there's parameter settings that only work well when combining them with other parameter settings. So when trying one of them in isolation, it might look badly, but when combining that with something else, it might actually start looking great. So yes, I mean, this is incorporated into your approach, and it's an important component. So it's a great point. All right, other questions?
If we have a document that proves to be effective, from like Stack
imitation learning in this setting, because this is kind of very similar to, an imitation learning type setup in reinforcement learning, where you have like, in this case, like a supervised, kind of data set of like what expert action would be given the state, right? So
yeah.
How does this relate to that? And is like
That's a
You
great
think,
question. That's a great
there's
question.
opportunities there?
That's a great question. So imitation learning has been proposed in the context of database tuning. And so basically here, the idea would be like to try to observe what are those human database administrators doing and trying to imitate that somehow. I mean, one first point is the question is, what do we want to imitate? I mean, if we believe that some of those tools can already beat the average human database administrator, maybe you don't even want to imitate that. On the other side, what could be useful are methods that somehow try to leverage information or things that you learned from other databases, for instance, in order to try to somehow transfer that to the current context. So at a high level, your question is about like exploiting new sources of information in order to make this even more efficient. And I believe that there is opportunities to do that. Actually, on this year's CIDR conference, there has been a lot of work on transfer learning for query optimization and for database tuning, which tries to learn something on one database or one system and then transfer that to a different database or a different system. I think that this could be combined with this approach and it could potentially increase, likely, I believe it will increase performance even further than done right. Yeah, that's a great point.